So in this video, we're doing the first part, our first lesson in the chapter 5, which is focusing on trigonometric functions. So I would say that in the fourth chapter, we were focusing on trigonometric expressions. We never really talked about trigonometric functions, maybe very briefly, but chapter 5 is really where we focus on trigonometric functions. And in fact, you've learned about trigonometric functions in grade 11. But just in case you forgot, we're going to basically talk about some of the same relationships and introduce a few extra concepts. So in grade 11, we definitely learned about sine and cosine. Okay, so we're going to use that reference point and build on that. And we also had our angles expressed in in degrees instead of radians. So in this lesson, of course, everything's in radians, but you know what? They're exactly the same as what you did last year. So let's fill in these ratios. Hopefully you don't need to refer to the video. Oops, yep. Okay, so I'm glad I get that 2 pi 0 and sine 0 is also 0, because these two angles are coterminal. Let me just verify. So this makes sense because this is quadrant 1 where sine is positive. This is sine where sine is positive as well in quadrant 2. Quadrant 3 is negative. Quadrant 4 is negative. Perfect. Everything checks out. So now let's do cosecant. So from sine to cosecant is pretty easy. Just take the reciprocal of all the ratios. So undefined. I'm just do these ones. Okay. So here's 2, 2, negative 2, negative 2. This is going to be 2 root 3 over 3, 2 root 3 over 3, negative 2 root 3 over 3, oops, 3, negative 2 root 3 over 3. Let's clean that up. All right, so hopefully you got the exact same ratios as I did. And please, no calculators here, because you should be able to find exact values of all these angles. So let's do the graph. Sine x and cosecant x. So they gave us a scale. So pi over 12 and half here. Oops. So I'm going to graph sine x first. So root 3 over 2, if you punch in a calculator, is about 0.87. So that is going to help me plot the point, because you might not know the approximate value of root 3 over 2, and that would be problematic because it'd be hard to plot that point. So let's say about 0.87. So if this is 1 over here, 0.87, somewhere like that. That's not very perfect. But it has to be symmetrical though. And that theme of symmetry is going to really come back to us when we talk about graphing trig functions later. All right, it looks pretty. So they didn't restrict the domain of sine x, so I am just going to draw arrowheads. Ooh. So try to make a nice, smooth, symmetrical wave. Just like what you did in grade 11. I know the angles are expressed in radians, but your curve, your wave, your sine function does not change shape. Okay? Beautiful. So that's sine x. And what we're going to do is graph cosecant x. Now cosecant x is going to have some vertical asymptotes, because where it used to be 0 is now a vertical asymptote. That's what we learned in chapter 3 when we talked about rational functions. when we're connecting polynomials with rational functions. This one you can't see very well because the vertical asymptote is on the y-axis. All right, so this is, we'll use 2 here. 1, 2, and then the reciprocal. So this one is approximately 1.15. The reciprocal of root 3/2 is approximately 1.15. So 1.5, let's say somewhere about there. Okay, so you have one invariant point because the reciprocal of 1 is still 1. Okay, well, you have one invariant point from 0 to pi, but they're actually infinite invariant points because sine x is equal to 1 and -1 at infinite values of x. I'll talk about when they occur, but there are infinite times where sine x is equal to 1. Alright, let's do the branch over here from pi to 2 pi. So here's -2, -2, -1.15, -1.15. Okay, something like that. So this is in line with what we talked about in chapter 3 with rational functions. So reciprocal of positive stays positive, negative stays negative. Big magnitude or large magnitudes become small magnitudes, and small magnitudes become large magnitudes. So what we said was small numbers become big numbers and big numbers become small numbers. But you really want to focus on the magnitude and not big and small. Okay, so here negative stays negative, so something like that. Actually, that was not good at all. That was really bad because it doesn't exceed, or it doesn't go past -1. We'll talk about that later, but you should. Where is -1? Let's see if I can reach it. I won't be able to get to it. It's okay. You'll just see a part of that graph. And over here, you'll see part of this side. Okay. So there's your sine x graph and your cosecant graph. Beautiful. So it really helps if you remember what you did in chapter 3 when you took the reciprocal of a polynomial function, whether it's reciprocal linear, reciprocal quadratic. The idea is pretty much the same. So one more time. Positive stays positive, negative stays negative, small becomes big, big becomes small. Now, I want to say how I knew my mistake over here. I can't, for example, y cannot be a value of -1/2, not for cosecant at least, because you're taking reciprocal of values between -1 and 1. So you're never going to get a y value of -0.5, for example, if you're playing with y values of -1 to 1 from sine x. We'll talk about that when we go over the range or all the properties of sine and cosecant. So sine, domain of sine, that was not a very pretty bracket, not a very pretty one. So all real numbers. Maximum value is 1, period is 2 pi. Last year you would have said 360 degrees. X-intercepts, I'm going to save that to the very end. Range, -1 to 1. The minimum value is -1. The amplitude, so we talked about the amplitude in grade 11. The definition was half the distance between maximum and minimum values. The formula would be max value minus min value divided by 2. So if you did the math, 1 minus -1 is 2, 2 divided by 2, 1. The y-intercept of the sine function is 0. Before I forget, I want to mention we're going to do all 6 graphs for the 6 different trig functions. You should definitely memorize, of the 6, the 2 you have to memorize is sine x and cos x, because those are the ones we're going to focus on in this unit. Not to say the other 4 aren't important, but sine x and cos x are, I would argue, are the most important for our unit. So hopefully you can memorize the shape of the wave. And plus, like I said, we did it last year, so the graph should really come back to you. Okay, for x-intercepts, a lot of students write 0, pi, and 2 pi. Now, 0, pi, and 2 pi would be correct if I restricted the domain of sine x, but I did not restrict the domain of sine x. Sine x could be any value, like x is any real number. That's what we said for the domain. If that's what we said for the domain of sine x, then please don't say the x-intercepts are 0, pi, and 2 pi. There are an infinite number of x-intercepts. So how do you write all those different x-intercepts in one line? So what you do is see if you can determine whether there's a pattern here. So 0, pi, 2 pi, 3 pi, 4 pi, 5, those are all going to be x-intercepts for the sine function. In fact, you can even say -1 pi, -2 pi, -3 pi, -4 pi, -5 pi, and so forth and so on. So if you think about it, what we should write here for the x-intercepts of sine should be k pi. Okay? Now, there's a big restriction we have to write for k. K can't be any real number. No, 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 no. K has to be an integer, right? What are integers? 0, 1, 2, 3, and the opposites of the whole numbers, like -1, -2, and -3. So this is how you express all the infinite number of x-intercepts. K pi, where k is an integer. Alright, so let's do cosecant. Cosecant has a domain. Actually, I'm going to save this one. This one's interesting. So I will write the range. So y is either less than or equal to -1, or y is greater than or equal to 1. Minimum value, a maximum value not applicable. So because it goes to positive infinity, it has no bounds. So not applicable, or you can write none if you want. Period. Since the values of cosecant x come from sine x, the period of 2 pi, the period of sine x should match up with the period of cosecant x, because I'm getting the output values of cosecant depend on the output value of sine. So if the sine values are being recycled every 2 pi, then should we not say the same thing for cosecant? Amplitude. Since there's no max and no min, you really can't say anything about amplitude. X-intercepts. This one's interesting. None. There are no x-intercepts. Y-intercept. The y-intercept is also none because there's a vertical asymptote at x equals 0 for cosecant x. Okay, so what about the domain? So there are an infinite number of restrictions. Well, where are these restrictions going to take place? These restrictions take place when sine x is equal to 0. So you're going to write x cannot equal to k pi, where k is an integer. And of course, x is a real number. So if you understand the x-intercepts of the sine function, then you should understand the restrictions on the domain of the cosecant function. They have to match up. So for the next page, it's really repetition of the first page when we focus on the sine function and the cosecant function. So I would like you to pause this video and try to fill in the table. So the exact values for the cosine function and secant function. And when you fill in all the cells of the table, try to generate the graphs of the cosine function and the secant function. Okay, so hopefully you got the exact same ratios as I've shown you from the table. It's really good practice later on when we solve trig equations in this unit. So hopefully your graph matches up with my graph. So the cosine function you should be already very familiar with because we graphed that many times in grade 11. And if you look at the cosine function, that wave looks very similar to the wave that you worked with in grade 11. Okay, it's no different whatsoever. I know that the angles are in radians instead of degrees, but that does not change the shape of the cosine function whatsoever. And the sine wave and the cosine wave, those two graphs, basically the shape is exactly the same, but the starting points are very different. So if you think of the y-axis as where the wave starts, then the cosine function starts at a maximum value, whereas a sine function, it starts at the middle of the wave. Okay, so there's two big ideas for this lesson. First of all, you need to be able to know how the graphs of all 6 trig functions, how they look. Okay, so knowing how all 6 trig functions look is, I guess, one of the objectives here. The second objective is to know the properties of the 6 different trig functions. So, you know what? Let's go fill in the characteristics or the properties of the cosine function, and from there we're going to generate the secant function. We do cosine first because that's something you're very familiar with. So the domain of cos x is all real numbers. Okay, we're not going to restrict the domain. We're not going to just focus on 0 to 2 pi. The range, the y values bounce from -1 to 1. The maximum value, of course, is 1, and the minimum value is -1. Period is 2 pi. Last year you would have said 360 degrees. The amplitude is 1. Just like I said, for the sine function, max minus min divided by 2. X-intercepts, I'm going to save that at the very end. Y-intercept is 1. So if you compare this, so far what we have for cos x, the properties of sine x and cos x are very much the same. And you should expect that because, like I said, the shape of the two waves are identical. It's just the starting point, okay? So cosine starts at a max and sine starts in the middle. So x-intercepts, just like last time, we want to devise a method to express the infinite number of x-intercepts that occur for the cosine function. So we got the first two that you can see on the graph. Pi over 2, 3 pi over 2. Okay, what's after 3 pi over 2? It should be 5 pi over 2 because the spacing between the subsequent x-intercepts of the cosine function, there's pi radians that separates the two. So if the first one occurs at pi over 2, then the next one will be 3 pi over 2. And the one after that will be 5 pi over 2. And so forth and so on. So let me help you out. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2. So hopefully you can devise the pattern. It's 2k plus 1 times pi over 2. Why 2k plus 1? Because if you saw the pattern, you'd say 1 pi over 2, 3 pi over 2, 5 pi over 2. Those are odd multiples of pi over 2. So how do you express an odd number? Take an even number and add by 1. You could subtract by 1 too, I suppose. But the big idea is that the x-intercepts are odd multiples of pi over 2. And just like last time, k is an integer because you can also say -1 pi over 2, -3 pi over 2, -5 pi over 2, and so forth and so on. Okay, but the big idea is odd multiple of pi over 2. I would argue this relationship is not as easy to see as what we devised, what we saw with sine, because sine is a multiple of pi. So yeah, I'd say odd multiple of pi over 2 is harder to see than just a multiple of pi. But anyways, that's a relationship for the x-intercepts, or the infinite x-intercepts for the cosine function. All right. And if you're having a hard time grasping this and you're asking why is this notation necessary, it's because there are infinite number of x-intercepts. So you have to devise a fancy way of writing it. So you have to introduce some interesting notation to be able to express all the infinite x-intercepts that the cosine function has. Okay, enough said. Let's generate the properties or characteristics of the secant function. So domain, actually I want to save that for the very end. So the range. Guess what? The range of the secant function is the same as the range of the cosecant function. So y is less than or equal to -1, or y is greater than or equal to 1. And of course, y is a real number. Maximum value, not applicable, or you can say none, because it goes towards positive and negative infinity, the asymptotes. Okay, period. You're recycling values from the cosine function, so the period of secant is 2 pi. Amplitude, not applicable. X-intercepts, none. The y-intercept is 1 because reciprocal of 1 is 1. So now domain. So you say x cannot be any odd multiple of pi over 2, because those are where the zeros of the cosine function take place, and reciprocal of 0 is undefined. There you go. So, two big things. We've done the four of the 6 trig functions, but let's take a quick break. The big idea here that you need to know is are the graphs of the 4 trig functions we've done so far. I know we've done 4, but focus on sine and cosine. Those are the big ones. And to be honest with you, if you know the graph of sine and cosine very well, then you know the graph of secant and cosecant very well. So know the graphs of the 4 trig functions we've done so far, and also know the properties. Try not to memorize them. Try to really be able to derive them. Like for example, if you know the x-intercepts of the cosine function, then you should be able to come up with the domain of the secant function. Try not to memorize them. Even if you ask me, like what's the domain of secant x, I will revert back to the zeros of the cosine function. That's how I will come up with that domain. Okay, let's try to work with tan x and cotan x. Okay, so time to move on to the last 2 trig functions. So remember, big idea, know how the graphs look and the properties of each trig function. So pause the video once again and try to generate the ratios and the graphs. Okay, so hopefully you're done the ratios and done the graph. So quadrant 1 is positive, quadrant 2 is negative, quadrant 3 is positive, quadrant 4 is negative. I made some mistakes here. I added some cells here that weren't necessary. Okay, so hopefully you have the exact same ratios as I do. Now, this graph, I chose to color code it because it was I didn't want you to be confused as to which one is tan and which one's cotan, because there's a lot of vertical asymptotes, and some of the asymptotes are for the tan function and some of them are for the cotan function. I didn't think there was much confusion with the sine graph and cosecant graph, but if you're confused with those graphs, you could draw on the color code them. But I really didn't feel that it was necessary for those 2 graphs because they're very different. Whereas the tan and cotan, I can see why you can get confused with one with the other. Anyways, the purple one is tan and the red one is cotan. Yeah, we're going to talk about why there are so many vertical asymptotes. Because, yeah, there are infinite number of vertical asymptotes, and we want to devise a method of expressing all the vertical asymptotes that take place for tan and cotan. Okay, so let's go for it. So we're going to start with tan. Now before I even fill in any of the characteristics or properties for the tan function, I want you to remember to draw the graph of the tan function. It would be really beneficial to remember what tan x really is. What is tan x? The quotient identity says tan x is sine x over cos x. So if I am very good with the sine function and the cosine function, then that will really come in handy. Okay, so let's talk about the range first. Let's do the easy ones and then we'll talk about the hard ones. The range for the tan function, all real numbers. Okay, that could be very apparent when you look at the graph. Okay, the tan function has a domain of all real numbers. What about the maximum value? Well, since the range is all real numbers, guess what? There is no max. Okay, not applicable. What about the minimum value? Not applicable. The range is all real numbers. Now the period of the tan function, be careful. The period of the tan function is not 2 pi. The period of the tan function is pi. Now you might be wondering, why is it not 2 pi? Well, you can think about the unit circle and the cast rule. Quadrant 1 and quadrant 2 is where tan is positive and negative respectively. And 3 and 4 is positive and negative respectively again. And if you look at the unit circle and the triangles that you draw, really the behavior of the ratios from quadrant 1 to 2 are exactly the same as the ratios from quadrant 3 to 4. That's why the period of the tan function is pi and not 2 pi. Okay, amplitude, not applicable. I have no max value, I have no min value. X-intercepts, we're going to save that one too. Y-intercept of the tan function is 0. Okay, so the two we haven't filled in is the domain of the tan function and the x-intercept of the tan function. So you know what, I'll go with the x-intercepts first. The x-intercepts of the tan function. Let's look at the graph. What are the x-intercepts of the tan function? So just in case you don't see the pattern, because to be honest with you, the pattern is very similar to what we saw with the sine function. If tan is sine x over cos x, tan x should be 0 when sine x is 0. So to know the x-intercepts of the tan function, you just need to know what the x-intercepts for the cosine function is. And we talked about it earlier. So I'll show you the graph of the sine function again. And what did we say? We said that the x-intercepts of the sine function are k pi, where k is an integer. So that logic should be exactly the same as the logic here. It should be k pi, because if sine x is 0, tan x is 0. Now what about the domain? When is tan x undefined? Well, since tan x is sine x over cos x, tan x is undefined when cos x is 0. So the restriction should be when cos x is 0. So the restrictions on x should be exactly the same restrictions we had for secant, because secant is undefined when cos is 0 as well. So what do we say for cos? Is an odd multiple of pi over 2. All right, so it's really helpful to know that, or to remember that tan x is sine x over cos x. Who knew? Quotient identity, so useful. So use the exact same quotient identity to help us out here. Cotan x is cos x over sine x. So I'm going to skip domain and x-intercepts and come back to them. So range, all real numbers, no min value, no max value. Period is pi. Be careful, don't say 2 pi. Amplitude is not applicable. There's no max, no min. Y-intercept is none because you have a vertical asymptote at x equals 0. So let's do x-intercept again. So for what values of x is cotan x equals 0? Well, cotan x is equal to 0 when cos x is 0. So the zeros of cos x must match up with the zeros of cotan x. So when is cos x 0? Odd multiple of pi over 2. I forgot to mention, double stroke z is the symbol we use for integers. Okay, so last one, domain of cotan x. When is cotan x undefined? Cotan x is undefined when sine x is equal to 0. So all those vertical asymptotes, they occur when sine x is equal to 0. When is sine x equal to 0? It would be really helpful if you knew this graph of the sine function. So if you don't remember, refer back to the first page of this handout, which focuses on the graph of the sine function and the cosecant function. So x cannot be k pi, where k is an integer and x is a real number. All right. So the big idea of this lesson, or the two big goals, is to know how the graph of the 6 different trig functions look and know the properties of all 6 trig functions. So I would really not recommend you to memorize all the properties, because I personally don't memorize them. I just generate the relationships from scratch. So how do you generate the relationships from scratch? You need to focus on the two graphs. You need to focus on the sine graph and the cosine graph. Luckily, those are the two graphs that you learn in grade 11. Why should you focus on sine and cosine? Well, think about it. From the sine graph, you can generate the cosecant graph. And from the cosine graph, you can generate the secant graph. But not only that, if you know sine and cos very well, you should be able to generate the tan graph and the cotan graph. Okay, and the same could be said for the properties. Knowing the properties of sine and cos will be very, very helpful to determine the properties of tan and cotan, as well as cosecant and secant. So I would highly recommend you to master sine and cosine first if you're having trouble with this lesson.